Differentiation using power rule is very simple. You just apply the formula and you get the answer. Well, we will go through the example of using the formula later on. But before that, let me try to explain to you what differentiation really is. At its core, differentiation is a method to find a gradient of a line in a graph. Well, we have learned about gradient in the lower secondary school, and it is defined as change in y over change in x. So, the gradient m is equal to delta y over delta x. We would normally describe gradient as the slope of the line. More intuitively, if we put ourselves at the foot of the line and try to walk up the line as if we are walking up a hill, then the higher the gradient, the harder it is to walk up the hill. So for this line, I call it manageable. I can probably hike up the hill with some considerable hardship. So the gradient of this line is lower than the previous one. But with this slope, I call this crazy. I will need to have a rope to hike up. So I call this slope as having the highest gradient as compared to the previous two. Now, this shows a horizontal line. So there is no change in y. And as such, dy over dx is equal to 0. So the gradient is 0. Like we are walking in a shopping mall, that is. And this one now, this is like we are walking downhill. So the gradient is negative. Differentiation, which is also known as derivatives, is essentially gradient of a line, but it goes beyond the gradient of straight line. We can use derivatives to describe gradient of a curve like this one. To calculate the gradient of a straight line is fairly easy. You pick up two coordinates, note down the y and the x coordinates, find out the difference in y and the difference in x, and we calculate the gradient. But to calculate the gradient of a curved line like this, that poses some challenges, because gradient is different on the curved line at different points. For example, M1, M2, M3 are three different values of gradient. We would normally, for graphical reason, represent gradient as the gradient of the tangent line to the curve, which is a straight line that just touches the surface of the curve. But the technique of derivative is very special. It is able to define gradient of a curved line by a formula derived from a concept called limit. Take a look at the curve again. If we take two coordinates on the curve and note down the value of x and y and calculate delta y and delta x like we would do to any straight line, then we can get the gradient. But this is not a straight line, this is a curved line. So we can only get a very rough estimation of the gradient. What if we could zoom in to very close and make delta y and delta x really small, almost at microscopic level? Then we can see the curve like a straight line. Take a look at this again. Delta y and delta x are approaching zero value. Very much like people thousands of years ago. They thought that the earth is flat because humans are just too minuscule compared to the size of the earth. Well, even though the earth is round or spherical, we perceive it to be flat because we are just too small compared to the size of the earth. That is the same with the curve. We know that it is a curve because we see it as a curve from here. But if we enter the world of the microbes, then we can see it as a straight line, because microbes are just too small to know that it's a curve. So derivative from first principle, we would write it to be like this. Well, we do not have to worry about this right now, unless if you want to go one level deeper, which I encourage. Just search for this topic, which is differentiation from first principle, and you will able to get the resources necessary for you to learn. But for our purpose right now, it is sufficient for us to memorize this formula. So let's use this formula for a few examples. I have purposely put the formula in color code so that you can identify a, n, and x. The first example, fx is equal to 2x cubed. So the value of a is 2 and value of n is 3. When you apply the formula, then you take up the n, which is 3, multiply that by 2, and then x, the index of 3, minus 1. then you get 6x squared. Next example, fx is equal to 5x squared. So the value of a is 5 and n is equal to 2. So f prime x, that is a symbol for derivative, is equal to 2 times 5x to the power of 2 minus 1. So f prime x is equal to 10x. The next example is slightly more complicated. Fx is equal to 5 over x squared. Now we have x squared as the denominator. Then we need to apply the index rule to bring up the x up here. So it becomes 5x to the power of minus 2. So now we can identify that a is equal to 5 and n is equal to minus 2. So we bring down the n minus 2, multiply by 5, and then x to the power of minus 2 minus 1. So the answer would be minus 10x to the power of minus 3. So bring down the x again using the index rule. F prime x becomes minus 10 over x to the power of 3. Next example, fx is equal to 3 square root of x. Now we're going to apply the index rule again because square root of x is equal to x to the power of 1/2. So we write down fx is equal to 3x to the power of 1/2. So now a is equal to 3 and n is equal to 1/2. So to perform differentiation, then 1/2 times 3, then x to the power of 1/2 minus 1. And that becomes 3x to the power of minus 1/2 over 2. But the final answer is we bring down the x and become 2 over 3 square root of x. So that is the 4 examples on using the differentiation formula. The baton is with you now. Do a lot of exercise. With enough exercise, you will be able to do differentiation with your eyes closed. This brings me to the end of my explanation. I hope you enjoyed this video. Thank you. I'm signing off now.